Hi there guys, well welcome back. We've just done 4E, we're working now towards 4F. And you can see that what I was talking about in the previous exercise where they were giving you this formula all in terms of A, so they're saying f of A plus h in brackets, take away f of A, all divided by h, and we're limiting as h tends to 0, now turns into, so rather than that particular point, A comma f of A, they're now using the general point as we differentiate this with respect to x from first principles. Now, by the way, they call this with respect to x. Sometimes you might see written down R, WRT with respect to. It's just saying that that's our variable which we're doing this process with respect to. Okay, so the next little formula box here is essentially the same as the previous one. And you'll notice they're saying as well, this also can be called f dash of x or f prime of x, or dy dx is how we pronounce the dy divided by dx there. But it's a thing, it's a definition, it's not a fraction there. So dy dx is talking about the gradient function for our y or f of x at any particular point for x, it will then give you the gradient. Okay, so there's that. Now there's this kind of little extra sort of caveat here as well. And let's just take this one and read it through. It says, well, if f dash of x exists, we say that f has a derivative of x or is differentiable at x. And a function is said to be differentiable everywhere if the derivative exists for all x in the domain of f. Now, that's kind of, I think that's just like a little extension to say, you know what, we had that previous formula which was working for particular points. Now, as long as this is working for every point over our domain, then we can say that this f dash of x exists for all points, then this function is differentiable everywhere, if you can say that. I think they're kind of just saying, well, is this function differentiable everywhere? In other words, does the derivative exist for all given x? So I think I wouldn't worry, you're not going to get tested on that, but I just think that's it's just saying that a function is differentiable everywhere if the derivative exists for all x in the domain. And therefore, we can use as well this new formula with x in rather than a in. That's the way I read it, at least, anyway. Okay, so couple of questions here. We've got example 13 and 14, so not an awful lot before we get to the next exercise. So this one says, given that f of x is equal to the square root of x, find the derivative. So we're going to do this via first principles again. So we're going to say that our f dash of x, and we're going to say, so this wants our gradient at x is equal to 9, essentially. So ultimately, we'll need to substitute in x is equal to 9. So gradient function is equal to the limit as our h tends to 0 for our function here. Now remember, we're going to substitute in x plus h. So we've got the x plus h, let's just put it as a square root like this, to the power of a half, and then take away x to the power of a half, and then divided by our h in this case. Okay, so when we're looking at this, we're thinking, well, how do we simplify this function in the middle here so that we can do some cancelling of h or try and take this a little bit further? So you may be thinking, well, we've got a rational power here on a binomial expression where we could expand this out. But the problem that we're going to have there is that that gives you infinitely many terms. So that's going to be a bit of an issue. So we've got to be a bit creative with this one. And remember that we can times this by its conjugate, and then maybe we could get rid of these to the power of a half. So let's actually go back to the other format. Let's say this, take away square root of x, and if we times that by x plus h minus the square root, sorry, plus the square root here, then your square root should disappear, because you're going to end up, obviously you've got a minus b, a plus b, multiplies out to give you a squared, and then minus b squared. So we're going to need to use the surd conjugate in this case. Now, I mean, I could have kept it in that format like that, but I think that was kind of a dead end in a way, because I was thinking of using binomial expansion with rational powers. And in fact, I think it's like this. Okay, so now let's times the bottom by that as well. So we're going to get h, and then that's times by the square root of x plus h, and then plus the square root of x again. Okay, well, that's the limit as h tends to 0. Now, when we multiply out the top part there, again, we're going to get this squared take away this squared. That's just a difference of two squares format. So we're going to get x plus h take away this times this. And now you can see that we're going to just end up with h on the top. And if we end up with h on the top, that's going to cancel with the h on the bottom there. Now, it takes a fair bit of creativity, I think, to see that in this case, and practice as well, and remembering that if you've got surds, then you can use the conjugate of that expression in order to multiply those together. Remember, conjugates exist not only for complex numbers, which we were using them for before, but also for surds. Okay, so now we're also getting h cancelling there. That's just going to leave us with 1. And so now we've got 1 over this thing here. Okay, now if we got 1 over that thing there, that's going to tend to, as h tends to 0, this is going to tend to 0 here. We're going to have 1 over 2 lots of the square root of x. Okay, so that's going to be our derivative for this one here. Okay, so let's just think about that again. So let's think, if we had x to the power of a half, we times by the original power, and we reduce that power by 1, we're now going to have times by x to the power of minus a half, and that's exactly what we've got here. So if you know the rule which is coming up next, and a lot of people will do, that with polynomials you just take your power and bring it to the front and reduce the power by 1, as I mentioned briefly in the last exercise, and you can see that we get exactly this thing again. So we're happy with that. That verifies the situation. But now there is our f dash of x. Now all we need to do is substitute 9. So remember, of course, that the this disappeared because we actually essentially put in h is equal to 0. When it tends towards 0, this is going to tend towards 0 here as well. We're going to end up with this. We're limiting towards it. Okay, so last little thing then, f dash of 9. Substituting in 9, we're getting 1 over 2 lots of the square root of 9. Remember, it's not plus or minus the square root. This is just a surd. This is not solving an equation with squares in. So now we're getting 1 over 6. And that should be our final answer. Okay, yeah, we're seeing we're getting 1 over 6. Okay, example 14. Okay, example 14 here. There's a particle moves in a straight line so that its position from its starting point at any time t in seconds is given by s is equal to t squared, where s is in meters. So s often stands for displacement, and t is your time in seconds in this case, and your displacement is in meters. Okay, so essentially this thing is moving up or down a line. So there's your s-act. This is your, it's moving up or down a line, that's fine, but I suppose we would put that in as s here and t here. So that's what we're doing. It's essentially moving up and down this line over time. So, we're not quite sure how that's looking. Doesn't look too complicated though. Like an x squared graph, just like that. That's 3 lots of t squared is going to be an x squared graph. Okay, and presumably we can't go backwards in time. The particle passes through a point P when t is equal to a, and passes through point Q when t is equal to a plus h. Okay, so you can see how they're linking this to our formula. So find the average speed of the particle between these 2 points. Now, average speed is talking about, again, the change in your displacement divided by your change in time. That's your average speed. Now, obviously, we need to bring those things together. So bring the 2 points together, so make h as small as possible to find the instantaneous speed. But at the moment, they're only asking for the average speed. So the average speed is talking about the change in displacement. So that's going to be 3 lots of a plus h squared. So that's putting it into here. No limits that we need to consider here. We're not bringing h to 0. These are just 2 separate points in time. And then take away 3 lots of a squared, that particular time. A is a particular time. And then the change in time is just h. It's the difference between a and a plus h. Okay, so no limit in this case. This is just an average speed between those 2 time periods. So its average speed is change in distance divided by change in time. And a lot of people would have been using the formula distance over time for a lot of years to equal to your speed there. The only difference here is that we're talking not only about speed and distance, but we're really talking about velocity and displacement, because S is displacement, it's got direction. Fact is, though, everything's positive in this case and everything is increasing, so we can actually call it speed as well, because we know that everything is positive. Okay, so right, otherwise we get average velocity. Okay, so what do we got then? So if we multiply out the top, well, we can factorize out the 3 if we want to start off with, and we're getting a squared plus 2ah plus h squared minus a squared. I've just factorized out the 3 as well, dividing by h, and so the a's are cancelling there, and we can see this is equal to 3, and we can cancel on h. If we factorized out the h from the top, we can cancel that h, and we're just going to end up with 2a plus h on the top. So that's the average speed, and obviously that's going to be in terms of a and a plus h, and also having used our formula for displacement as well. So we can't really say much more than that. It's dependent on a and a plus h, and it still is. Okay, so there we go. There's our expression. And then it says, well, let h tend to 0. So now we're talking about this situation where we're saying this function here, when we're taking a limit as h tends to 0 of that function. And so that function is now actually reduced down to 3 in brackets 2a plus h. And now this is going to give us our instantaneous speed when it passes through P, because point P is when time is t is equal to a. So when we bring these 2 points together, h is going to disappear there, if you like, as we bring these things closer and closer together. And so this is going to end up being 0, and we'll just be left with 6a. Okay, so that's your instantaneous speed. Now, you probably know that one already, of course, because if you've got s is equal to 3t squared, then your ds dt is equal to 6t. And again, that's the formula which is coming up next, which is telling you to essentially times by your power and reduce your power by 1. And there we go, we're getting this function here. That's your ds dt, which is the same as this thing here as well. Okay, so this is also equal to ds dt, but at the particular point where t is equal to a. Okay, so that's why we're getting an a out there, and we're getting a 6t out in the kind of the rule version of doing this. Okay, but we've followed this through like they want us to at the moment, given what we know about differentiation from first principles. Okay, and in an exam situation, I think average speed, you'd still have to set up like this. So you can see that they're trying to lead you through exactly the same steps. Okay, well, maybe the exam question would actually say, yeah, prove this, prove that the speed is 6a, but actually it does say hence deduce, so therefore we know that we do need to use differentiation by first principles in this question. Okay, well, let's have a little look at what they've done. They've sketched this one. Did they ask us to sketch it? No, they didn't, but there we go. It's just a 3 t squared graph, that's all. And they've come up with the points, they've come up with the average speed there, come up with the expression, and they've let h is equal to 0. They've done exactly the same. Okay. So a little point at the end, it says, if you are asked to find the derivative of a function from first principles, you can simply use this formula here. So where you normally have the formula with a in, now they're putting the formula with x in. And by the way, the denominator of this formula here, where it says x plus h minus x, really can be just left as h. Now I'm just going to look at this to see the version they give you in the formula booklet as well, but just to say that 3f, 4f, sorry, misspeaking here. So 4f is just 3 questions there before we move on to the next little bit. And the next little bit looks not to be the rule still. It's that they're now talking about continuity and differentiability as well. Okay, so it's still a bit more theory really before we get into the rules. Okay, well, let's just look at the formula booklet and see what they give you here. Let's see the formula booklet, and let's see where it is. Doesn't appear to be turning up there just yet. And there. Have I missed it? Like I must have missed it. Here we go. Derivative is given to you here. There's a formula here. Got the integral formula as well. And here we go. Differentiation f of x, derivative of f of x from first principles. This is what you'll get given in your exam. So let's just zoom into this one here. And we can see that it's telling you that you get dy dx is equal to f dash of x. And they're putting in x, not a, like in that first, the previous exercise. And they're putting in h on the bottom. Okay, well, you can see actually there's lots of standard derivatives which you're able to use ultimately, but we'll come to those, at least some of those later in this chapter. Okay, well, thanks for listening. Good luck with the exercise and hope to see you next time.